2. We are reviewing for the final today. I'm going to give you some logistical information about how the final will play out, and then we'll move into which lessons are likely to be covered. Okay, so Gracie, hi. She suddenly needs attention. The final will work just like it did for our last midterm, what I call term. I usually refer to the midterm by the period of time that the lessons were originally taught. So the midterm that we took in early spring covered the winter lesson, so I'm calling that the winter midterm. But the important thing is that we took this one under quarantine and we're taking the final under quarantine, so it'll be the same process. I'll drop the envelope by your house, you will do the test. It will be the same type of test. It will be 10 questions of 5 points each. I will grade it. I will get back to you right away with your result. Good girl, Gracie. She's lying down on top of my foot. Okay, so that will all be the same. There will also be 3 review problems to cover the 3 weeks. Since the last midterm, it's too complicated to try and do the review problems every week, which is what I would prefer to do. So I'm just going to do all 3 of them at the same time we do the midterm, which is, we did a catch-up last time, so it'll be the same. So you'll actually any material. It'll be 13 different lessons tested. Does that make sense? Well, you can't say yes or no, so I guess I just have to hope you do. 13 different lessons tested, okay? So if you want to think of it as a 13 problem test, you can. You know for sure that these 3 review problems will come from the new lessons. The 10 questions on the test are going to be a mix of old and new. I will tell you more about that in just a second when we get to talking about the content on the test. All right, so this is all the winter midterm. That'll be the last thing. I will give you, after the midterm, right, so I'm going to bring the midterm, the piece of papers, I'm going to bring them back, I'm going to review them. Then what I'm going to do is put together a final packet of your review problems, your test. Lydia, I'm calculating a grade for you because I know that for your credit requirements, you need that. I'm pretty sure Dr. Westcott requires a grade. Jayla, if you like, I can calculate a grade for you too. We can text about that. In fact, you can pause me right now and just text me whether or not you want to get a letter grade for this class. It's totally up to you and your mom, whatever would be helpful. So I will bring, and so then I will give you your final grade if you want it, plus your, which will include the last midterm, the final, all of your review problems. I'll give you a summary of your scores so that you can see everything in one place, and I will drop that off to you within a week after taking the final. Housekeeping, and then I'm going to talk to your mom to make sure that you have all the information that you need to get your credit for this class. Since you're both doing different classes, I won't talk too much about that, but I will talk to each of your moms to make sure that they've got everything they need to present for your credit, which is weird, I know too, because nobody's meeting in normal ways. So anyway, we'll deal with that. So there's our process for the last. If you have any questions about this, if you have any questions specifically about what the final is going to look like, feel free to message me and ask me, and you can always pause me right now and message it. Okay, so let's now talk about the content. Which lessons are going to be on the final, right? That's what everybody wants to know. Okay, the first thing I'm going to tell you is that there will be content from the new lessons that we've covered since the midterm, which are only 3 weeks worth, right? So I'm going to quickly blast through those. Lesson 122 was about intersection and union between sets. We also talked about Venn diagrams. 121 was about rational inequalities. And that's where we learned the little trick about how you can't multiply by 2. You have to do it x minus 2 quantity squared so that you're not flipping the inequality sign. We did some age of word problems. Billy is 10 years older than Sissy. In 5 years, he'll be 30 times older, whatever. That's not a real problem. I'm just, you know what I mean. 190. It was absolute value inequalities, which we've done quite a lot of. But in this particular lesson, we used the set builder notation, right? The thing where integers equal z. Lesson 118 was log equations, and I brought in John presented that in a different lesson, but I introduced it with lesson 118, so it all goes together for 118. 117. Set builder notation. That is where we learned about this other weird way of presenting the same information. 116. Permutations. Probabilities. 115. Exponential equations. That's where we used logs to solve problems about science and business, specifically interest. How much interest would you get? Oh gosh, I'll go back. You remember that lesson. 114. This was nonlinear inequalities. This is where we divided the graph up into the 4 regions, the A, B, C, and D, and then you had to pick which region contained the solution. Was log. It's where we first met logarithms, so it was the log basics. 112. Oh my gosh, I'm just going to have enough lines. This was quadratic inequalities. These were the less than. Remember lesson 110, which fell under the midterm, the greater thans, and then we skipped up 2 lessons and then we did the less thans. And then 111 is 3 statements of equality. And that's where we were solving 3-part. We had 3 equations. We had to solve them together. Okay, now, so these are 15 lessons that we covered since the last midterm. I could easily write a test of 10 items. I could even do the 3 review problems, because this is 15, right? 5. No, it's not even that many. It's 5, 10. Is it exactly 13? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. No, it's not even. But I'll tell you what, I'm not going to pull all 13 questions out of these lessons because John's a smart textbook editor. He knows that the vast majority of students will never finish the entire textbook in 1 year. Most people just don't have the focus and discipline to stay on it. So what he does is he packs the most important content into the middle of the book, and then here at the end, he introduces some, what I would call nice to know, but not necessarily need to know topics. So I don't want to focus all 13 of my questions on these lessons. I'm going to show you which ones I'm most interested in. These age word problems, those are good. The laws of equations in 118, where we were actually solving, those are good. Exponential equations, those are really good, you guys. You're going to be so far ahead in the future math that you take. And then the three statements of inequalities. Those are topics I am highly likely to lean toward, okay? Those are in the new lessons. Now that's not to say I'm not telling you which ones are my favorites. And honestly, I think so. Make sure you know those really well. So that's all the new content for the midterm. This test, because it is such a small handful of lessons from the back of the book, I am going to definitely pull from other older lessons, okay? And I'm going to give you some guesses as to topics. I'll provide some lesson numbers. Go back and fill those all in because I don't know all of them. But I'm going to give you some ideas, all right? Way back in lesson 5, this is the lesson, and this is the topic, okay? Let's make a chart. Lesson 5, there were a variety of word problems that you supposedly would have learned in your previous algebra. You may or may not have. I'm going to draw from the commonly tested in tests like the AccuPlacer and the SAT. Lord only knows if you guys are going to be taking tests like that. But if you say you know algebra, you definitely need to know how to do some of those problems, all right? Some of the additional problems, there were the dirt problems, distance equals rate times time. We reviewed all of these. You know what, while we're talking, I'm just going to scramble around and find the lesson numbers for these. These are what John calls uniform motion problems. They're what I call dirt problems. Let's just see if I can find where we encountered those lovely devils. Uniform motion problems, here they are. It was lessons 22. Remember there were 3 different types. There's the Lord of the Rings kind, that's the first one. Then there's 29. This is Lord of the Rings. This is Titanic. And then the third kind is 34. I'm still developing my story on that because I'm teaching these to the younger students. This I'm pretty sure is Robin Hood. If you've seen the Disney Robin Hood, well, in any Robin Hood, but particularly in the Disney one, there's lots of people chasing around and getting head starts and starting from the same place. This third type of dirt problem matches to Robin Hood, so that's what I'm calling it. The delicious chemical mixtures. Chemical mixture type problems. These are called word problems, but it's a variety of different kinds of problems. The chemical mixtures, there's an A and a B. So this is type A and this is type B. A is lesson 52 and B is lesson 61. I would definitely know those. Really big headache. On the other list, the really big asterisk, boat in the river. I don't know why I'm hyphenating this, but I just like the way that looked. That was lesson 92. Okay, definitely want to cover those. What else do I have here? Lesson 100, you guys, I know you hate it. This is graphing parabolas. 70 was abstract equations. All right. And 71 is quadratic formula. And then, let me find, I want to get there. You know how when we sometimes solve quadratic formula and we get the complex roots? Right, we would get imaginary numbers. I'm not sure exactly where that one shows up. I'm quickly glancing through. I'm not seeing it right off the top of my head. It might be, I think it was the second part of a lesson. That is what I'm thinking. I'll find it. I'm not going to look anymore now because I'm distracted and not paying attention. All right, so this is a list of additional problems that I would make darn sure that I could do because I'm likely to pull from these. All right, I'm not going to test you on scientific notation. I'm just glancing through the table of contents and anything else. This will do it. This will do it. This is a lot of good, tough problems. Make sure you can go back and do all of these, okay? The third thing I asked you to do is give me a list of lessons that you would like to have retaught. And I got 5 lessons from Lydia, and I'm going to quickly go through those now. As the last part of this lesson, Lydia, you asked some really good questions, and I would include the lessons that you've asked about as potential questions on the test, which is not to say you caused your own problems by giving me these, Lydia, but some of them have some really good questions in them. So I'm going to go through your suggestions for things that we additionally study right now, and I'm going to just do one problem of each. I'm going to do one of the harder problems and make a few comments on that. So, without further ado, the first lesson that Lydia asked about was lesson 39. There are 3 topics in this: difference of 2 squares, parallelogram proof, and rhombus. I'm going to tell you right now, don't worry about the parallelogram proof, and don't worry about the rhombus part. The only part in this that you need to really focus on is the difference of 2 squares. And this falls under the general category of factoring. And what it says is that when we see an expression and we recognize that it fits this pattern, it's a square and a square, we can factor it automatically. We don't have to do any sort of like, well, they have to multiply to this and add to that. We just find what A is equal to and what B is equal to, and then we can factor it like so. You don't have to think about that. You could just know that if you ever multiply those 2 binomials together, you're going to get that. It always works out that way. And so here is an example where I can show you how this works. It says solve 81 m squared minus 25 equals 0. It says solve this by factoring. Okay. So, at first you look at this and go, factoring? I don't know how to factor that. That looks really hard. You sit there for a minute going, what? This is hard. I don't want to do this. Why am I doing math? I hate my life. Just kidding. But then after you look at it for a minute or two, you go, wait a minute. 81, that's 9 times 9. That's a perfect square. M squared, that's a perfect square. And 25 is 5 times 5. That's a perfect square. Oh, okay. Into your head, because you wrote it on the inside of your notebook cover and you remember it forever and always. And you realize that, oh, okay, in this case, If this is a squared, then a would equal 9m, right? Because when you square it, the 9 would become the 81, the m would become the m squared. And b, we don't have to worry about the minus sign, right? Because that's always supposed to be there. B squared is 25, so just plain b must be 5. So now we can rewrite this expression as 9m minus 5, 9m plus 5. And then we just tack on the equal 0. Okay? The plus can come first and the minus can come second. Or you can do it the way I wrote it here with the minus first and then the plus. It doesn't matter because when you multiply, order doesn't matter, right? Okay, so that is the hard part of this. Let me flip and recreate. This was the last step that we had on the previous problem. Now, if we're multiplying two things together and they equal 0, that means either 9m minus 5 equals 0 or 9m plus 5 equals 0. So two things multiplied together equal 0, one or the other has to be 0. So we consider both sides. This 9m equals 5, m equals 5 over 9, and this one, when we move it, we get minus 5 over there. So it's minus 5 over 9. That's our final answer. That's the difference of two squares, and that's lesson 39. Lesson 49. Is about linear intercepts and transversals. Linear intercepts doesn't even have a problem that goes with it. What I'll review on that is that we're going back to our friend y equals mx plus b. This is what we call the linear intercept or the y-intercept. This one is the slope. And what's going on in this particular lesson is that if we know a pair of points, x and y, and the slope, we can fill those three in and solve for the y-intercept. And that is what is going on in that problem. Transversals are a geometric concept, and this is a really good problem. This is one I would definitely consider putting on the test. What happens is that we have these transversals, right? There are two lines that we have two parallel lines, and then we have a line that cuts through the two of them, and we know it makes this pattern of smaller, larger, larger, smaller, smaller, larger, larger, smaller. It makes that pattern of angles, right? The larger and the smaller angle always add up to 180, and they add up to 180. Anytime you have a straight line, right, you can imagine the different pairs. And so it's super easy to come up with the angles based on that. Now, in this example, we're told that the larger angle is 153 degrees. We're told that this angle is z. We're told that the lengths of these sides are 7, A, B, and this angle is P. And we're supposed to find sides A and B. Now, how the heck are we going to do that? This is example 49.1. This is a really good problem. I would love to put something like this on the test. What we need to do is use our sine, cosine, and trig functions to solve for these missing sides. If we only had this angle, we could do it, right? So we have to go back down here where we actually have a hard number in our angles, and then we have to follow it up. If this is 153, we know that these two have to add to 180. So that tells us that z equals what? 47, right? 47 degrees. No, that's not right. That's too many. 27. Yes. Okay, 27 degrees. if z is 27 degrees, then p is also equal to 27 degrees. Okay, so now we've got an angle and we've got one side. This is the hypotenuse, right? So now we can use this to use our trig functions. Oh my gosh, I'm so excited. So what that means, let's see. Sine, cosine, tangent. That's one reason I really like this problem, is because it allows us to use this business again. Oscar had a hold over Arthur. All right, to get the opposite side, we're going to need to use sine. So to get b, we're going to say that the sine of 27 degrees equals b over the hypotenuse, which is 7. And then we would rewrite that as 7 times the sine of 27 degrees will equal b. And then you use your calculator to calculate that, and I'll give you the answer so you can work that out. It's about 3.15. And then to get a, that's the adjacent side to this angle, so we'll use the cosine. And we'll say that cosine of 27 degrees equals a over 7, and then we'll cross multiply and say 7 times the cosine, of 27 degrees equals a, and I'll tell you the answer and you can figure it out yourself, 6.23. Okay, so those are the answers. That's a really good problem, I love it. Lesson 15. No, it's not 50, it's 59. 59 is the notorious experimental data. And draw a question on this for the test, but I really would love to take away the stigma that I know these problems have created in your brains. Better if you imagine yourself taking a science class and you're in the lab and you have to do the same experiment multiple times and then draw conclusions about your results. So what you do is you do some experiment that involves taking copper and then turning it into bronze, all right? So that's your science. You took copper to start, and then you did something to it, and you turned it into bronze, and you recorded how much copper you started with, and then how much bronze you got in the end. And you varied it, right? First you started with, it looks like maybe 7 kilograms of copper. You used that a couple times. Then you went up here, you used 10. Then you used what, maybe like 14, and then 15. And then you got different amounts of bronze in as a result. So you get out your notebook and your lab book. I always love lab books, they're cute. And you made this graph and you recorded this. You didn't put the line in there yet. And then you looked at that and said, is there a relationship between all these experiments? Are they telling me something about a general rule I could make and turn it into bronze? And you say, it looks like my results are pretty consistent. So you drew this line through here to say, it looks like this is the general rule, right? And I can use my experiments to kind of create this general rule, this line that passes through pretty much through the center of all of these points, right? It doesn't hit every single point. Here's a few that are above the line. Here's 1, 2 that are below. But this is a pretty good line. And you just drew this, right? Another person could have drawn it slightly angled, as long as it looks like it kind of passes through this crowd of points. So now what you want to do is you want to find what is the equation of this line that you made, because that will describe the relationship between the copper and the bronze. So what you do is you find 2 points that lie on this line, and like I said, if you're a smart scientist, you will draw your line so that it definitely passes through 2 crisp points. I think this looks like a really crisp point, right? The line goes right through the corner of the graph paper, and this one looks good. So we can use those as our points to find the equation of this line. The first one is 5 and 5. Let me show you that again. Here is the, can you see this? I hope so. Let me move it up a little bit. It's 5, and then I come over this way, it's this line, and I realize, oh, this is going up by 10, so that's actually 5. So that's 0.55. This point here that goes through that circle, that looks like 15 and 40. So I'm going to use that as my second point. So now I have 2 points that lie specifically on the line that I drew through those lab results, right? They're not the points of the lab results, they're the points that my line that I created crossed through. They're on the line. And now I just need to solve for y equals mx plus b. I need to find the b and I need to find the m, right? M is the slope. We have a formula for that, right? y2, whenever we have 2 points, we can solve it with this formula. We can come up with the slope if we know 2 sets of points. So I'm going to call this one x1, this one y1, x2, y2. It doesn't matter which ones are the 1s or the 2s, as long as within each pair they match. Okay, so now I'm going to bucket this because the minuses will make you crazy sometimes. y2, 40, y1, 5, x2, 15, x1, 5. This becomes 35 over 10, which we reduce to the decimal, 1 because it's super easy, and 2 because it's science. Science likes decimals. Mathematicians prefer fractions, but scientists like decimals. So when we work in the world of science, we simplify. I covered up my decimal. We simplify to decimals. It doesn't have to be that way, but it does work nicely. So now we've got our m, it's 3.5. So now we can plug that, we're going to take y equals mx plus b, I'm going to rewrite it here. We can put this new calculation, that's our m, so I'm going to put that right there. Then we pick one of our pairs of points and plug that in for x and y. I like this one because I can't screw up which one's x and which one's y. And now we solve for b. This is 5 equals, and then I'm going to do 3.5 times 5, 25, 15, 16, 17. And I put the decimal in before I finished. That was not the right way to do it, but it gave me the right answer. 17.5 plus b. Now I subtract to isolate the b, and I get minus 12.5 equals b. So that's what goes here, minus 12.5. Now I've got an equation, y equals 3.5x minus 12.5. I'm almost done. Instead of saying x and y, we copy the elements from our chart on the x and y axis. So there's no rocket science to this. Copper is the element written on the x-axis, and bronze is on the y. That's the only thing you need to know. So I'm going to say b, because bronze is on the y-axis, equals 3.5 times copper, and John reminds us that copper is abbreviated as Cu, minus 12.5. That's our final answer. Part of me might want to put that on the test. That's a good one. Squares, yes, as well. That's a good one. Okay, 49, what was that? Oh yeah, I liked this one too. I'm going to put a star on that one. I'll show you, see? So all three of these are really good problems. 39 was the difference of two squares. 49 was the calculating the missing information on the triangle here. That's the transept. It's called transversals. And that's what I'd actually put the star by. And then there's lesson 59, experimental data. Okay, next topic, there's only 2 more lessons, we're almost done. Lesson 70, oh, this is one that was on my list too. Advanced abstract equations. P.S. back on lesson 59, yeah, it was 59. There were 2 other topics, don't worry about those. The experimental data is by far the one that I want you to focus on. Advanced abstract equations are when we have only letters and we're solving for one of them. Abstract means it's letters, really no numbers. Equations tells us we can solve. This was on my other list of good to know problems. I'm starting it. Here's the way it works. John gives us a string of letters. Wait a second, I don't want it up that high. XP equals M times the quantity look at this giant mess, okay? When we just see this, we have no idea what to do with this. We need John's instruction, and that is, he says, find C, okay? I circle it so that I remember what the heck I'm doing. Well, look, C is buried way down here. Oh my gosh. Well, we've got a lot of work that we need to start worrying about isolating the C. The first thing we have to do is get rid of the parentheses and the denominators, all right? So I'm going to take it in that order. I'm going to first distribute. I'm going to multiply this M across. It's not bad. It's over a 1. There's no denominator other than 1, so it's not going to change things too much. So I'm going to write XP equals BM plus AM. I'm keeping it alphabetical. All right, beautiful. I like it so much better already. My second step is going to be to eliminate the denominators. All right, it looks like demons, it's not, it's denominators. Okay, these are my steps. All right, so what is my least common multiple of these two? Well, I can't add anything, so I have to multiply. So it's going to be P times the quantity 1 plus C. That means I've got an equal sign here, so I'm not going to multiply top and bottom. When you have an equal sign, you multiply every term by the least common multiple. So I have to do it on both sides, you guys. Oh my gosh. Every term gets it. Over here, nothing cancels. So I'm going to have x times p squared times 1 plus c. Oh my god. Over here, now this is where the denominators will cancel. So this is going to be BMP, right? Because the 1 plus c's cancel. And over here, the p's are going to cancel. So this is going to be plus AM times the quantity 1 plus c. Now I have to distribute again, right? Because I had a quantity in my denominator, it does it again. So now I have x p squared plus x p squared c equals BMP plus AM plus ACM, okay? Woo! That was a lot. Now we can focus on getting our C terms. What I write for this is swim desired terms, right? We're going to get the C's on one side. So I say, since there's 2 over here, let's subtract the ACM from both sides. And let's subtract the xp squared from both sides. Okay, that gets rid of him. That gets rid of this. Now we have both of the c's on the left side, and we have all the non-c's on the right side. So I have xp squared c minus acm equals bump plus am minus xp squared. All right, whew. We're getting there, you guys, we're getting there. And now we have to divide away, we have to factor out the c, xp squared minus am, right? I take the c out of both. And then we divide away this beast. And if we did it right, this whole thing equals c. I don't want to rewrite it again if I don't have to, because every time I rewrite it, I risk making a mistake. So now I'm going to double check it in the book. John says he says mbp plus ma minus xp squared over xp squared minus am. He's got letters within the terms in different orders, but everything's the same, the signs are the same. So that's a big fat yay. I have not been smiley facing my answers. That's a really, really good problem. Definitely potential. And then the last lesson that Lydia asked for a review of will not be on the test. It's lesson 84. It's important to understand it, but it's kind of a theoretical type of problem. So it's lesson 84. And it's about types of solutions. To systems of equations. Okay, so let's say we have a nice little system of equations, y equals x plus 2 and y equals minus 2x minus 1. And we know how to solve these. There's substitution, there's elimination. We can solve them by graphing. One time, quite a few years ago, I'm not sure why I was on the bus one day, and I was sitting behind two girls who were obviously college-age students. It was on a route near Edmonds Community College. That's what a lot of the bus ridership around my neighborhood is doing, is going to classes. And they were conversation about which their preferred method of solving systems of equations, which they like better. They were so cute, I died. Okay, if you graph these two lines, you're going to get something that looks kind of like this. I'm not going to be super precise. I'm not going to take the time. But they're going to cross at one point and have one solution, and that is what the vast majority of the systems of equations we've been looking at do. They give us one solution, okay? So these two lines in our system of equations create one single solution, right? Now, let's imagine a second scenario. And I'm going to have another system of equations. They're different, they're not the same. But when I go to graph these, I realize, wait, let me put arrowheads on these too, it looks better. When I go to graph these, I realize, wait a minute, this is the same line. Because if you take every term in this bottom one and divide it by 2, you get the top one. So this is two two ways of saying the same thing. So when you graph both of those lines, you get the same line. So this, we have an infinite number of solutions. Okay? In type A, we only had one solution. There's only one place where they cross. In B, we've created the same line. I'm going to do this. So this is two lines. This is the same line, and it creates an infinite number of solutions. That's our B. Now, I'm going to squeeze C in here because I don't want to turn the page. With C, let's have y equals 2x plus 2, y equals 2x minus 2. Now, these are different lines. They're not the same line like we had here, but when we go to graph them, we notice something interesting. Pretend they're perfect. They are parallel lines. Oh, that makes sense because look, they have the same slope, but different y-intercepts. That makes sense then, that they would be parallel lines. So these have no solution, because you know what? These two lines are never going to touch. They're parallel. They go on forever, perfectly straight, pretend, and they're never going to touch. And so we're never going to have a place where they intersect, so we're never going to have a solution. And we can always recognize this because there are parallel lines. Okay? Now, this part is the part that I hope you will find fairly easy to understand, right? One solution, infinite solutions, no solution. The vast majority of the problems we've dealt with fall into this. These are kind of weird things that we haven't seen a lot of before. But what mathematicians have done is they have come up with two weird words to describe systems of equations. I'm going to write them in this box because, again, I don't want to flip. One word they talk about is consistent. They talk about what's a consistent system of equations. And in this one, our examples A and B are considered consistent. It has at least one solution. Consistent means it has at least one solution. So, okay, this has one solution. This has an infinite number of solutions. C rather, this one has no solutions. So, inconsistent, consistent, is a word we can use to describe system C. Okay? The word consistent means it has at least one solution. Make sense? And then there's another word. I'm running out of space so desperately. Dependent. A system is dependent when one of the equations contains all the solutions of the other. Okay? So dependent would be this one, when one equation contains all the solutions of the other. And then independent, the opposite, would be A and C. The hardest part of this lesson is remembering these two words and what they mean. All right? It's really hard, it's really obscure, it's very theoretical. What's much more important to me is that you understand how there are three different types of systems and that we have these fancy names to describe them. I will not ask you this on the test, I promise. All right? That's lesson 84. Okay, there's a quick review of the 5 lessons that Lydia asked about. They turned up some really good potential problems for the test, so that was time well spent. Thank you. Jayla, if you have any questions, please shoot them my way and I'll do a video of your questions. And I will talk to you in the messages. Thanks. Bye, guys.